Yes, I think, can you all hear me? Is the sound good? Okay. Yes, my name is Daniel Cremers. I'm heading the chair of computer vision and artificial intelligence right over on campus here in informatics and math department. So just a few hundred meters from here. The area I work in is the field of computer vision. For those who are not so familiar with computer vision, it's an area that's becoming increasingly important these days. Back when we started, for example, when I started as a professor in Bonn in 2005, we started working with, as you can see, Daimler on driver assistance. At the time, this was a fairly small niche area. A few people were interested in it. But as you know, nowadays it's getting a lot of interest, a lot of attention in the media, in the public, partially because a lot of the technologies we've been developing over the last decades are starting to really work in practice. For example, what we developed back then is we put cameras in the car like so, and a lot of the research we do is funded by the European Research Council, and as you know, they always want high-risk research, right? I never know what that means, high risk, but I think, throwing your PhD students in front of a driving car, if that's not high risk, then I don't know what is. Right? And so obviously the idea is to then make sure the car autonomously stops. If you have a bug in the code, then, well, next PhD student, I guess. What we developed are techniques like these that allow you to recover the 3D structure from these cameras, and not just the structure but also the motion of things here, color-coded. Red means moving. There's a lot of little arrows that tell you where different structures move over time. And you can imagine understanding the 3D world in front of the car and estimating the motion allows you to even predict what's going to happen next. And these predictions are vital for avoiding accidents and saving lives, because the longer you can predict into the future, the more you can obviously avoid accidents. And here this motion allows you to say this: if that obstacle keeps going with the same velocity, it will be in the driving corridor in the next few seconds, and then you can engage in a braking maneuver, etc. This is a long time ago. This was 2008, more than 10 years ago. The field has moved. The field is growing very fast. Just to give you an idea, last year I organized one of the 3 top conferences in computer vision, the European Conference in Computer Vision here in Munich. And when we started organizing it, the previous venue, 2 years before, the previous ECCV had 1,500 participants. So I booked a place called Gasteig here in Munich, nice concert hall. It seats 2,200 people. So I figured 1,500, 2,200, there's like at least 700 more. That should be more than enough. Well, I was completely wrong. We ended up getting 5,000 registrations, so more than 3 times the previous venue in Amsterdam. And we could only seat 3,300 because then we were completely booked, so we had to basically shut down registration once we reached 3,300. The remaining 1,700 all ended up on some waiting list. So this is the situation we as computer vision community face year by year. The conferences sometimes double, sometimes triple in size. It's a scary growth, and honestly no one knows where this is heading. I myself have been at TU Munich for 10 years and built up the chair of computer vision and AI. It's one of the largest academic research teams in computer vision, and so we have about, 25 PhD students and postdocs, master students, etc. So it's a fairly big team, and invariably we work on quite a range of topics. It's a bit hard to summarize all the things we work on: autonomous robots, more mathematical topics on optimization, also machine learning, deep neural networks, things like that. But then also the topic that I want to look into today is the topic of camera-based reconstruction of the world, because this is most closely related to the topic of this workshop. The topic is one that you're all familiar with from everyday life. You walk around this world and you see the world with your eyes from different vantage points. And the question is, can we, given all these 2D observations of the world, can we somehow recover the underlying 3D structure? There's different ways to phrase, we just talked about it, there's different ways to represent 3D geometry. Often it's done in my field with point clouds, but you can also consider it as a dense surface representing the object. And as such, the problem you are trying to solve, mathematically speaking, is a problem of infinite dimensional optimization. It's important to visualize what does that really mean. You know, for most people, like my daughter, she's 9, and she says, "What does that mean? 4 dimensions? You know, the world is 3D." She understood that, but 4D, she didn't. You know, she still doesn't understand. And so when the public hears infinite dimensional, that typically throws off most people. But it's very, very intuitive. Basically, you know, let's say we want to reconstruct Beethoven here. We start with a wild guess. We say maybe a sphere. And then we start perturbing that sphere to better match the observations. You know, how many ways are there to perturb a sphere? Essentially, you can take every point on the sphere, and there are infinitely many, and you can move it in the normal direction and get a new shape. And since you have, and each of these points is a separate degree of freedom to your shape optimization problem. And since you have infinitely many points on the sphere, it's an infinite dimensional optimization problem. In practice, it means the solution spaces are very large. The space of conceivable 3D shapes is very large. In computer science, people don't like continuous worlds, infinite dimensions. They discretize the world, and they chop it up into lots of little so-called volume elements, like in this cube. And then for each volume element, you can say, very simply, is this volume element, say the one down on the left here, the little white one, is it object or background? 2 choices. That's super simple. But let's say we consider 2 voxels at the same time. Both can be object, both can be background. One can be object, one background, one object. So with 2 voxels, just the 2 voxels can have 4 possible configurations of object background. And with every new voxel you consider, the number of configurations doubles, right? As a result, if I have n voxels, then the number of possible configurations or reconstructions on that lattice is 2 to the power of n. Because with every voxel, it increases by a factor of 2. For a computer scientist, this is obvious. It means you have an exponential growth. It means the space is very large. The other day I gave an evening talk in the German Museum, and since the public doesn't necessarily know what exponential growth means, I decided, okay, let's actually crank it out. Specifically, let's say for a volume of 512 by 512 by 512 voxels, so not very large, but enough for Beethoven, right? For that voxel, it's 2 to the power 512 cubed. And so, as I said, my daughter, she's 9, she's in school, she has a calculator. And so I said, can I borrow your calculator? And so I typed that in, 2 to the power of 512 cubed. And you're laughing, you must know what happened. The calculator said, it can't do it, it's too big. I was really disappointed. I don't know who designs these calculators. Right? I mean, for once I need one, I haven't used one for years, and once I need one, it doesn't even do a simple calculation. So what do you have to do? You have to do it in your head. It's actually not difficult, so I have no clue what my calculator is doing. I estimated it's 10 to the 40 million. And this took me, maybe a minute to estimate it's 10 to the 40 million. So the number of 3D reconstructions on that little lattice is a 1 with 40 million zeros. That's how many 3D models you can think of on that resolution. Now what we're asking the machine is, which of these is the best one? Now you could say, why don't I try all of them and see which one works best? Well, no, not if it's 10 to the 40 million. Even if it takes you a nanosecond to evaluate each reconstruction, you would still wait until the end of the universe before this thing is ever done, right? So this is no way of going. And still, we want to get the best reconstruction among all conceivable ones. How can we do that? It's not a trivial challenge. Maybe a bit of how do we get 3D from images. The common way is to infer 3D structure by something called photoconsistency. So you go into 3D space, you assume we know where the cameras are, you can project points like the eye of Beethoven into images, and you can say this green voxel here is on the surface if I observe the same color in two views. Whereas points like the red one are likely not on the surface, because once you project into cameras, you tend to see different structures, so the colors tend to not be consistent. And this notion of color consistency in the projection into pairs of images, this can help me distinguish points that are on the surface from points that are not on the surface. And so what I do is I define what is called a photoconsistency function that checks for this color consistency for all voxels, the space of voxels. Mathematically, you would call it R3, the 3D space we live in. And then you have a photoconsistency for each voxel. And you can compute that. You can project into pairs of images, check for color consistency, and by convention, we would assign small values of rho to points like the green one, where the colors match, high values of rho to points like the red one, where the colors in the projection do not match. And once we have done that for all voxels, we can then cast the whole reconstruction problem as an optimization problem, where we say, find a surface S, a surface in 3D space, such that if once I aggregate these values of rho along the surface, all the points on the surface should be maximally color consistent, meaning they should all have a small value of rho, and hence the total, the sum over all these rho values should be small. And this is a way to cast reconstruction as an optimization problem, where now I say in the space of all conceivable surfaces, find the one with lowest cost. Now I can go ahead and take these 10 to the 40 million surfaces, right, and compute their cost and say which one is the best. Except it's not feasible because it's too many. And so this is an important challenge. How can we find the best solution, the provably best one? And this is not trivial, and we were fortunate to achieve a breakthrough in 2009. We were able to prove that for these types of cost functions, you can actually compute the provably best surface efficiently. Efficiently doesn't mean fast. It means it takes about an hour for the 512 cube resolution. But efficiently means you can provably get the best in finite time. You don't have to wait until the end of the universe. So 1 hour is a lot of compute, but compared to the age of the universe, I find it's actually not so bad. How do we do it? By a technique called convex relaxation. So rather than having a cost function in our space of solutions that is not convex, we show that we can replace it with an equivalent convex one. And convexity means that even in very high dimensions, you can find the optimum fast. I don't want to go into detail how this convexification is done. It gets rather technical and mathematical. But the key consequence is we can now take images, typically 20 or 30 images from different vantage points. Admittedly, we have to know where the cameras are stationed. And then we can compute photoconsistencies and then compute the provably optimal reconstruction. And that is the one you see here. So you actually see this evolution process where we go from a random initialization here to the optimal. And this process in 2009 took about an hour. The reconstruction is not perfect, but it's the best for this cost function that we considered. You can go further. I don't want to go too much into the math here because this is not a math audience, but you can actually compute the color on the surface. In fact, at the level of detail where the reconstructed 3D model cannot be distinguished by eye from the original one. And this is quite nice. It allows us to acquire 3D structure with cameras today at a level of precision that can easily fool the eye. In fact, we could show that our reconstruction of the color is even sharper than the camera images that you took from the bunny. This is something I think you know if you've ever seen these crime scenes shows on television, CSI Miami, CSI New York. There's always these, in almost every sequel they have, the license plate of the bad guy and it's kind of pixeled and blurry and you can't really see it. And then, the head of the police department says to the techie, "Can you zoom in?" Right? And then the techie always says, "Sure." And he hits a button and everything becomes super sharp. I don't know what happens when you watch this, but what happens to me for a computer vision guy, I always sit there thinking, I wish I had that algorithm. An algorithm that can start with a blurry pixely image and get something sharp. The truth is you cannot do that. You cannot hallucinate details out of nothing. So the question here is, how can we achieve this for a real world data set? It's because we see the same eye not once, but many times in different camera images. And we can exploit that redundancy and generate from several low-res images one high-res reconstruction. This is called super resolution, and in this setting it actually works once you have more than one image. But in the crime scene they only have one camera image, so there's something fishy there, I can tell you. Hollywood. There's more in Hollywood. One of the things you want to do for Hollywood, for example, and also for digital twins, you want to reconstruct humans, and even humans, how they act in time. And we can use exactly these techniques and film an action like this one from 16 synchronized cameras and reconstruct the whole action in time. We can freeze time. We can view it from an arbitrary viewpoint, and so this is often called, we can back project the textures as you see, and so we get a video. It looks like a video of the scene, except there was never any camera where we are stationed now, because we have a complete digital model of the whole action. The geometry, the motion, the colors, everything. We can even go in and change things. We could now change the illumination, we could change the textures, we could change all sorts of things, the clothing, etc. can be modified. Once you have a model, you can do so many things. Or just sports analysis. For example, you can film a rope jumping girl, and as you see, our methods are sufficiently accurate to recover the entire rope of the rope jumping girl just from cameras. And I can tell you, this is something that you can never do with laser scanners. I know laser scanners are popular to access geometry even at large distances, but if you want to resolve it in time like here, forget it. Because the laser has to scan line by line, cameras can acquire information instantly. Except they don't measure the geometry, they measure the color, but using this color consistency, we can recover geometry as I showed. There are special cameras nowadays, so-called RGBD cameras that have been around for nearly 10 years that actually measure the depths. Here is one, it's called Kinect or Asus PrimeSense. There's different companies that offer them. What we developed here is a technique, as you can see, that recovers 3D geometry and color in real time. On a click of a button, you just rotate around. It basically glues the depth measurements into a coherent 3D model, and then you can print it out on 3D color printers. I didn't bring any, but I have tons of 3D models of all my former students or colleagues. It got really popular at some point. The president of TU Munich wanted to get scanned as well. And I didn't feel like moving him on a chair like that, so sorry. Let me switch off the sound here. I hope this switches off the sound. Oh, sorry. I think that may be this. Sorry. So we developed a standalone scanner where you just click a button, you stand, and then there's 3 cameras that rotate around on this robot arm and in real time generate this colored 3D model. And this is a full body 3D scanner, so you can scan people. And that way you can get your own digital twin just on a click of a button. If you're interested in this, please come by. We have scanned hundreds of people. The other day, Angela Merkel came to visit, and I suggested that we could scan her because she was asking what kind of demos we could show, and that was the first one I offered. The Chancellor's office declined it. I don't know, maybe they had an inclination what I was going to do with the model, mass produce it. And you can, right? Obviously, we are, after all, we are an entrepreneurial university, right? And you can sell them, right, in the children's store for Christmas, a little, right between the Smurfs, you can have a little Merkel's, figure. I could have even colored her blue, you know, that's not the issue. It's easy. But I think they knew it was coming, so they preferred other demos. So what I talked about so far is techniques where we basically, for the rope jumping girl, we placed the cameras. We knew where the cameras were. For many applications, for example, if you put cameras on a car and drive around, you don't know where your camera was at any given time. And then this raises a very challenging problem, which in computer vision is called simultaneous localization and mapping. So that is, you want to estimate where's my camera and where's the 3D world. A problem that was addressed more than 100 years ago. I find that quite impressive. In 1913, an Austrian mathematician, Erwin Kruppa, proved that if you see 5 corresponding points in 2 images, you can actually estimate both the 3D structure of the points and the motion of the camera. Quite a pioneering result that paved the way in the 60s and 70s. You know, and this is impressive. He did that well before the advent of computers. You might wonder, why would anyone work on this problem if you don't have a computer to actually do things? They were doing things manually, you know. They had 2 airplane images, and they would say, here's the, you know, the tip of the church tower here, here's the same tip of the church tower in the other image. Once you have 5 corresponding points, you can estimate the motion of the airplane and the 3D structure of the church tower. And so this was done. Then in the 70s, 80s, people developed computer-based algorithms to follow in Kruppa's footsteps. And they took 2 images, extracted points, put points in correspondence, computed 3D structure. What we advocated over the last years is not to follow in Kruppa's footsteps. And this is always my recommendation to students, generations of students. Sure, there's pioneers, they did pioneering things, but you have to question everything. You have to always question, is this really the best solution, or is there possibly a better one? And one thing you realize when you switch on a camera, you're not in Kruppa's setting. The camera doesn't give you points, it gives you colors, brightness values. And it's not clear which of these brightness values should I select as points. And it's even less clear which point in one image corresponds to which point in another. This correspondence estimation is one of the nastiest questions to try to solve. And so what we promoted over the last year, or so, say 10 years, are so-called direct methods, where the aim is to go straight from your sensor data to a 3D world. The benefit of doing that is that you don't have an intermediate abstraction step, and so you don't lose in precision and robustness. Because any errors you make in the point extraction, the correspondence estimation, they will invariably deteriorate your performance, your results. And so one of the first direct methods we published was a technique that I called LSD slam for large scale. Yeah, you're laughing. You'd be surprised, you know, the name of an algorithm has a huge influence on how much people remember it. I didn't realize that until it took me many years to realize it, and then I said, okay, the next algorithm will give it a catchy name. I said, call it LSD slam. So, you know, my student Jacob Engel. And then he came back and said, but Daniel, that's the name of a drug. And I said, yes. It got really, so this is my most cited publication ever. I'm sure it's only because of the name. No, just kidding. I think the work is quite impressive. It was the first large-scale, real-time capable camera-based reconstruction. And you'll see in a second what we mean by large scale. So there's this work, there's a number of follow-up works. Here's an example where we took the subway station out here. We walked into the subway station, top left you see the camera input. With the points that we extract here. And you see it's a random handheld camera, and we can track it, see bottom right, over a very large distance, just one single camera, standard like you have it on your cell phone. And we can track it all through the subway station and around on the other side, and track the camera motion at such a precision that even after hundreds of meters, there's almost no drift. Almost means the bicycle you see in the image top left is actually reconstructed twice there. So there is a drift that is being created because from frame to frame you estimate how did the camera rotate, how did it translate. Obviously you make little errors, they accumulate over time into this drift. But it is only 2 meters on a distance of hundreds of meters. The question is then, how can we measure the performance? How can we really quantify this? And so what we did is we took, lots and lots of videos with different cameras, different lenses, some more fisheye, some more perspective lenses, like hundreds of minutes of video, very diverse environments, indoor, outdoor, faster motion, more rotation, slower motion. They're all very different, but they all share one thing. They all look back to where they started from. And like in the subway example, we can then determine what is the total drift. And we did that, and we compared to what's considered the state of the art, a powerful key point based, so in technique called Orb Slam, not such a catchy name I found. And ours is called DSO. Unfortunately, the follow-up, we couldn't find such a nice name, but it's also getting quite a lot of citations, so maybe it's not only the name. And what you see here is the different errors in translation, rotation, and scale, and the number of sequences where we achieved a certain error. And the simple message is you want to be in the top left corner of all of these plots, meaning you want to have as many sequences possible with as small an error as possible. And you can read these plots in many ways, but for example, you can say, what is the maximum error on the best 300 sequences? The competition, Orb Slam, has about 6 as an error, we have about 1. Meaning the error is reduced by almost an order of magnitude. And this is very important because in computer vision, in my field, if you have other challenges like object detection, detecting airplanes and images, if you get 0.5% improvement over the state of the art, you can publish a paper. If you're 0.5% worse than the state of the art, you can publish a paper, right? This is not 0.5% improvement. This is almost an order of magnitude better than the state of the art, because we are using directly the sensor data. Here's an application where we extended this to 2 cameras, put the 2 cameras in the car, and you can see we can drive around the block and recover large-scale 3D maps of the world in real time. And very important for automotive, at very low cost. Just 2 cameras. Not any super expensive LiDARs, etc. If you look at competitors in this field, companies like Waymo that are putting self-driving cars on the road, well, they have big LiDAR scanners on the roof. And just the hardware costs more than $500,000. So I'm saying, well, great, even if it drives autonomously, who's going to buy it? Right? And then they might say, well, we can get rid of the LiDARs. Well, then it doesn't drive autonomously anymore if you drop the LiDAR. Whereas what we are advocating is, why don't we use cameras to reconstruct the world at large scale, at low cost, for things like autonomous machines, autonomous cars, drones, you name it. For reconstructing our 3D world at low cost. Generating, if you will, digital twins of our world. Now, this would not be a computer vision talk if I didn't talk about deep neural networks. My community, everyone since 2012, it's all deep networks. In this area of SLAM, deep networks have to date not really achieved excellent performance. There's many reasons for that, but what we developed is the first visual SLAM technique that uses deep networks and actually boost the performance. Because you can tackle all sorts of problems with deep networks, but honestly, if the solution is not better performance-wise compared to previous methods, then what's the point? And most of essentially all deep learning approaches to SLAM up until our paper, they did not perform well. They showed you can do it with a deep network, you can train, etc., but the performance was so-so. Here what we did is we started with a deep network to predict from one single image the depths of the scene. This is quite surprising how accurately you can do it, and we outperformed in depth prediction the previous deep nets. here you see that you get a fairly accurate reconstruction of the depths from just one single image. And now we feed that depth prediction into a SLAM approach, and now we can recover similar 3D environments like you saw them before, except this is taken with only one single camera. So it's not using two cameras, but only one, meaning you just reduce the cost of the hardware by a factor of 2, essentially. And this is by far to date the most accurate single camera based reconstruction. We can compare. We did a lot of qualitatively and quantitative comparisons. This is some of the top stereo methods, so methods that use two cameras to reconstruct the world. Here's our one camera method with a deep network. And what you can see is the deep network can basically replace the second camera. And loosely speaking, what this algorithm is doing is, given the right eye, it hallucinates what the left eye would see. And it turns out you can learn that. And I think possibly that's what humans also do. Humans who only have one eye can typically perform quite as well as people with two eyes, because the brain compensates, it can learn. And lastly, you can use deep networks to also infer the semantic meaning. This is a project we did in Berlin. And this is why I was a little bit starting later. I wanted to add that video because I think it's very important for the audience here. We can recover very large environments with their semantic label just from cameras installed in cars. What we did is this is a startup called Artisans, where we develop both hardware and algorithms, and we deployed our camera-based hardware in a fleet of cars earlier this year in Berlin. We did 8,000 kilometers of driving all around, and basically in real time generated what you see here. Large-scale semantic 3D maps of our world, acquired in real time at very low cost. And this is important because cost means you can scale it up to very large environments, to very large 3D maps. And typically we can distinguish some 20 classes or more depending on what you want to distinguish. We typically distinguish what automotive cares about: drivable area, sidewalks, cars, pedestrians, cyclists, buildings, etc., vegetation. So to summarize, I talked about camera-based reconstruction of the world, how you can get provably optimal reconstructions, how you can get reconstructions of actions over time. I talked about 3D photography, how you can use depth sensing cameras to get, on the click of a button, you can get 3D copies of people, miniatures, fairly faithful, detailed copies, digital twins of people, even full body scans of humans. The same techniques can be used to acquire rooms as well, if you want. I talked about this challenge of SLAM, where you estimate both camera motion and 3D structure to get maximum precision of the reconstructions, real-time performance. And lastly, I talked about how you can leverage the power of deep networks to further boost the performance, both in terms of the precision of the reconstructions, but also in terms of extracting semantic information. Thank you.
We had a discussion earlier about how technology can be used for good purposes and bad purposes. I can imagine this would be fantastic voodoo dolls. If you hate your boss,
Yeah.
Put him in there and then use a lot of pins.
Yeah.
3D printed. Any quick questions? Because I know we're a little bit late. Yes.
Maybe one question: can you or do you combine your algorithms with other assumptions like physics or geometrical considerations? For example, that no object can fly in the air, or as Johannes introduced, that usually a floor is always a plane surface. Something.
So we talked about this right before the talk. This is something that I want to explore more in the future. Extracting not just the geometry, not just the point clouds, but the actual physics of the world. And at least in my area of computer vision, this is completely underdeveloped. And I think this is what humans do. For example, if I throw you a tennis ball, you can catch it in the air, right? What does that require? It requires for you to not only figure out the 3D structure of the ball, but to infer the whole trajectory before the ball even took it. So somehow we seem to have some form of physics engine in our head. And you know, when I was a kid, I spent most of my childhood doing ball games, soccer, basketball, volleyball, everything. And I was always impressed, even as a small kid, how someone, you know, across the whole tennis court can throw you a ball. And often it takes me fractions of a second, and I can sometimes even close my eyes and catch the ball. And then I thought, how is that possible? You know, what's going on in the brain? That, you know, not only the trajectory where the ball is going to hit, but also at what time it's going to hit. Because if you close the hand once it touches, you'll never catch it. You have to know beforehand when you have to close. And so all of that our brains do. And they don't infer just the 3D shape of the tennis ball like we do. That's like not how you should do it. You should infer the physics. Like the rope jumping out, same thing. You know, we as humans, we don't need 16 cameras to see there's a rope jumping up. You know, 2 are enough. Why? Because we know the world and we understand, and because we infer the physics. The elasticity of the rope, we can estimate masses, elasticity, forces, all of that. And how to do that from cameras is quite an unsolved problem. It's one thing that we're starting to do.
All right, thank you very much, Daniel. We are